Hello everyone, and welcome to tonight's presentation of OTF Connect, introducing number sense in algebra with the 4-part math lesson framework with Kyle Pierce. Thank you so much for joining us again tonight. This is the fourth in a 4-part series with Kyle, and all of the links for the other sessions will be shared with you at the end of tonight's session in the resource page that we create for today. Here's our map of Ontario showing where everyone is from tonight, which is really terrific. And on behalf of Syria Skirhan, who's the administrator and facilitator of the OTF Connect program, we are always excited to have you all here giving up some of your own time to learn more and cool and interesting things with and from your colleagues around the province. We do have Kyle presenting through application sharing tonight, so I am going to go ahead and pass things over to Kyle, and Roberta, I'll be touching base with you in the chat. And if anyone has any difficulties, just let us know in the chat. And again, we appreciate your patience and us getting started tonight. So thank you, and over to you, Kyle.
Okay, hi everybody. Louise, can you hear me?
Yes, I can hear you, but I do want to let you know that you are going to have to click that application sharing button, the big one above the screen again, perfect. And it should switch. There, perfect, thanks.
Excellent. Now the one question I do have for you, and I'll ask Louise, is can you see, I'm trying to hide the sidebar of all the slide deck. Can you guys still see that the way I have it now?
Just a tiny bit, about half the slides. It's not too distracting, although it looks like your slide on the right section of your slide is cut off a little bit by a long white strip, so you might have something else open on that side of your screen.
How about now? How's that working for you?
Nope, but you know what? It's very minimal. It's just the beak of our Twitter bird that's cut off, so I don't think that's going to impact things too much. So I say let's go with it, and if we notice we need something, then we'll come back to it. Okay, perfect.
Well, let's try like that. Let's see how we do. Okay, perfect. Well, welcome everybody. Thanks for joining me for continuation, the third part of our 4-part math lesson breakdown. And tonight we're going to be looking at number sense in algebra. I recognize some of the names in the room again, so welcome back to those folks who are joining us again. That's excellent to see. I will do a quick little recall for us from a couple of the previous sessions, and then I'll also be trying to scaffold to our next session, or this current session, I should mention. So we'll get started here, and hopefully our tech will be working for us in a favorable fashion. So let's get ourselves started. Last time we were together, we had discussed a few different things, and I was going over the two groups of students that I had been noticing or recognizing in my classrooms that were forming. And while I was calling these two groups the group that was good at math and then the group of students who weren't so great at math, what I found out is that many of those students who were good at math as well were also struggling with unfamiliar problems. And then when I did some deep thinking about this, what I realized is that in some cases I felt as though students were merely trying to memorize, and some students were better at memorization than others. And I was actually rewarding this because in many cases I was giving students test questions that looked like things they had seen before. And anytime I would give a student a test question that didn't look like an example from my textbook, an example from my note, or examples from the homework or homework type questions, or a sample problem from the textbook, typically students were thinking that this was unfair practice, that I wasn't actually teaching them the necessary steps in order to test on those topics. And when I really reflected on this, what I realized was that these students in the good at math group, because I was rewarding them for their memorization skills, ultimately they really did have a right to say that I was being unfair. And that's simply because I was changing the game, late in the game. So with 2 minutes left in the fourth quarter of a football game, I'm changing the game by adding that last question that is unfamiliar, that's challenging, and I wasn't doing this on the rest of the test. So what I've been trying to do is find ways that I can help students gain a deep conceptual understanding rather than focusing on familiarity and on focusing on students, basing what we are testing them on looking familiar to what they might have seen in their class notes or in their class homework. So moving on from that today, we're going to be taking a look at this concept and a little some additional concepts there. I also mentioned last session that we really need to focus on finding ways to take our new knowledge and help our students take their new knowledge and connect them to prior knowledge. So ultimately what I was trying to do is take this idea of the textbook and really break it down a little bit, because ultimately what the textbook does is it provides us as teachers a way for us to organize our lesson plans. It doesn't necessarily help the learner. It organizes things very nicely and silos them. But ultimately, instead of showing that interconnectivity of math, what we're really doing is we're breaking away and we're actually siloing these things and almost separating these different topics from one another rather than trying to show how they could build on each other and how they're all interconnected. So ultimately, what I've done is I did share out my vision for math education, and it looked like this. And we're going to build on this vision today and show you some of the ways when maybe ultimately what I want to do is I want to make all my math problems contextual. Now this isn't always possible, and we'll look at some scenarios today where it might not necessarily be contextual. However, what I still want to do is ensure that it is visual and that there could be some sort of concrete representation that's not abstract. And then finally, taking those two things, what I want to do is also model how interconnected the different parts of math really is. Okay, so ultimately we talked about the idea that if we do this, that we should be improving student confidence or increasing their student confidence, improving their perception of mathematics, and overall student success. So that's my focus in this past school year. And I've been trying to take what I've been using in my classroom, which I like to call the 4-part math lesson, but many of you may recognize as parts of the 3-part math lesson. All I've done is I've taken that action part and I've broken it down into 2 very specific pieces, where the first part is inquiry, where students are actually developing their knowledge through some sort of discovery. And this will look different, obviously, depending on the topic. And then finally, helping them make the connection so that they can consolidate their learning as you normally would. So we do have a little chat. Is that Louise? Yes,
no,
Louise.
My sincere apologies. I've just realized that we're still looking at the beginning slide, and as you've been talking, I know you've probably been moving through. Do you remember we had that issue last time as well?
We did. Okay, so I'm just going to have to run the deck then. I couldn't remember if running the deck did that or not.
Okay.
Perfect. Sorry, folks. Let's fire this thing up here. And all right, we'll start it right here. So we'll start it at the vision. And ultimately, how are we doing now, friends?
I'm still seeing slide 1. Esther, next time you suspect something, don't hesitate to jump in. Okay, slide 1. So you've hit play, so you've
yeah, I'm in the play mode here.
What happens if you just do page down and move through your slides that way?
On my end, it's saying hosting is paused. Hang on, let's see.
Okay. Oh, there it comes.
How does that work?
All right, now I'm looking at contextual, visual, and concrete, confidence, and interconnected. Okay.
Okay.
All right, folks, so you should be seeing things change and refreshing a lot. And so as soon as Kyle gets settled in one spot, then
okay, I think we're good to go from here. So can you see that moving, the slide deck moving?
Yes, but it's very slow and laggy, so I definitely recommend that you minimize the movement as much as possible.
Okay, perfect.
So it's
All right.
constantly doing a line-by-line refresh. So which one should we be looking at? Student success?
Yes, and I'm just going to flip over to the 4-part math lesson that we were discussing while we were on slide 1. Okay, sorry about that, folks. All right, so we've got some, I see woohoo from Sherry, so that's a good sign. Okay, perfect. Hopefully everybody else is with us, and I think we are ready to go. So let's take a look here, and yeah, so ultimately looking at the 4-part math lesson, I've just broken down a 3-part math lesson into two additional pieces, taking that action piece and breaking it down into inquiry and connections. And ultimately what we want to do is we need to now find a way to actually marry or merge these two, this vision and a 4-part math lesson. So what I want to do is just kind of share with you what that may look like in the classroom. When we actually go to kind of pull these things or kind of push them together or squish them together, I typically like to think that the minds-on is where you want to start setting the stage with that context, maybe with that visual or that concrete material, depending on what it is that you're actually doing. And from there, the connections piece will be where we're actually showing how interconnected our math is, so where we can connect it to other parts of the curriculum. It might be from the previous day, maybe it's from earlier in the semester, or maybe somewhere that we're going to be taking the course later in the year. For the inquiry piece, what we want to do is ultimately merge that in and try to get students working towards a new learning goal using their prior knowledge and their intuition. I very rarely use the word prior knowledge with my students. I'm typically talking to them, and I'm looking at a spelling mistake, which is also nice too. So intuition. All right, perfect. So, so prior knowledge and intuition, that's something that I'm finding to be very, very valuable. So looking at inquiry as a place where you're setting them up to be able to solve a problem without any new skills that I'm giving them. And students seem to really thrive when you tell them that they can solve this problem without any new sort of algorithm or steps or procedures coming from the teacher. Whereas when you do give steps and procedures first, you might see students kind of stopping because they're not too sure what they're doing or why they're doing it. So that's where I'm always trying to get my students starting anyway, really lower that, floor on the problem. And then finally, at the end of the lesson, we want to be consolidating their new knowledge, okay? So taking those connections and allowing them to do some practice by, maybe taking away some of the context, taking away some of the visuals, and getting them to do problems that may look more like what you may see in a textbook or what you may see on some sort of standardized testing. So we have been talking about this throughout, and today what we're going to be doing is taking that 4-part lesson and focusing it on number sense and algebra. Now, I think it's always useful for us to have a quick little chat about where number sense and algebra pops up throughout the curriculum. I'm sure we all realize that number sense comes up very early in grade 1, and I mean, I think number sense is happening even before students come into schools, but we see that quite often. And we also see it in the grade 9 academic course, and we still see it in the grade 9 applied course. So I like to look at K to 9, when we talk about mathematics, I look at K to 9 as kind of the most important math that students could still use to apply to their everyday life. And then after grade 9, that number sense strand sort of disappears. It's assumed knowledge. Students start going into grade 10, and they are to start thinking more abstractly, right? And starting to think of, more analytically. So for me, being a grade 9 applied teacher, I really see how we can make some connections to all the way down into some of the primary grades and help students kind of jump on that elevator and then slowly take them up to where we need them to be during our current courses. When we talk about algebra, patterning in algebra is a strand that exists all the way from grade 1. However, the word in grade 4, we start to see things such as, I believe it's unknowns and variables. So we're starting in grade 4 to really start getting kids to look at math a little differently. And I pulled out this one specific expectation in particular for us to see ultimately that we have students solving equations in grade 4 even though they don't realize it. I know that they're probably using a guess and check sort of system to do it, but when you see down near the bottom here, the blank times 4 equals 24, they're solving a simple equation. And that's something that students in grade 9 applied still struggle with. So today we're going to look at some of the ways that we might be able to demystify some of these concepts that students have been essentially practicing since early in their education. So as always, I like to begin with a minds-on, kind of introduce the idea of where we might start a lesson, get students, everybody kind of connecting with this. And what I like to do when we're talking about algebra in particular, but obviously number sense will fall in here as well, is taking the idea of multiplication and chunking multiplication into friendly numbers. Now, something I want to mention here is you're going to notice that 9 times 12, many of you might say, you know what, I already know the answer. I do have some grade 9 applied students who do know what 9 times 12 is, but not many. Many know some of their multiplication tables, but not all of them. And to me, that doesn't really bother me at all. I think that, if they don't have all of their times tables, I'd just much rather them be able to visualize it so that they could do something to help them get to the answer. So what I would like you guys to do in the chat window, it would have been nice to get you typing on the screen, but we're not going to have that today. I'd love for you guys to take a second and think about what are some friendly numbers that you could break 9 times 12 down into. And I know that may not be super clear with what I'm asking for some of you, but I like to just get kids typically up to the whiteboard, and I get them all standing at the front, and I like to see what they think about this. So go ahead and break it down into any friendly numbers that you'd like. The best part is there's no right way to do it. You can do it in a number of different ways, and we can see them coming up now. So I'll give you a second to do that, and then we'll do some discussion. I'm really liking Mary Jo's idea of taking 10 times 12 and then removing one group of 12. Surprisingly, I very rarely see students doing that, yet to you and I, that seems like a pretty logical thing. We know, most of us know multiplying by 10, we're just essentially adding a 0 on and then taking away 12. But a lot of times students don't think about that one, which is different or interesting. I see Aaron has 10 times 9 and 2 times 9, so breaking down your 12 into 10 and 2. Krishna has essentially what Aaron has, but in a less simplified way. Not a bad thing. I really like that. I see the same thinking in just a slightly different way or different notation. And Christian's going with the 10 times 12 as well. So lots of different ideas here, which I like. I'm really liking Diane as well as saying 3 times 12 plus 3 times 12. I'm assuming plus another 3 times 12 would be a very appropriate way to go as well. Awesome. Very cool. Now the funny part is if I get many math teachers in here and if I didn't tell you to chunk it into friendly numbers and I asked you to work this out, typically what I see teachers doing, and this could be 7 and 8 teachers that I work with as well, typically they start out with lining the numbers up with the 12 on top, 9 on the bottom, and then they start the standard algorithm. But as you can see here, you can really easily start chunking this thing down. And what I try to get my students to see is that this can be made very visual. I'm going to use the idea of 10 plus 2 instead of 12 simply because it is going to help me later with the algebra piece. I don't tell the students why I choose to do it this way. However, I try to get my kids thinking along the lines of showing a bracket, and ultimately it's to introduce the concept of distribution. All right, and distribution is something that students tend to struggle with. especially when variables are introduced. So just to make this a little bit more visual, when we go back to the idea of contextual, visual, and concrete, in this case, I'm taking something without any context, but I'm trying to make it visual, and I can help students see that 9 times 10, you can very, very clearly see that 9 times 10 plus 9 plus 2 will give us 2 separate chunks of 90 and 18, and we can then put those together and get a total of 108. So I get students thinking this way, and most students can do this. Sometimes they're not sure exactly what I'm asking for at first, so we help them along with, with trying to clarify what we want them to do, get them thinking of the visual of the multiplication table that they may remember from elementary school when they were learning, and then we get them into another problem. So I'd like you guys to try this one as well. We've got 13 times 15. What would be some ways that you could chunk this down into a more manageable numbers to work with? So give it a shot, and then we'll share it. Oh, that's awesome to see. I hear Aaron talking about the area model. Absolutely, it is well known as an area model. The only reason I use the word chunking is because I find that it's a friendly term for students. It's definitely not recognized by educators, though. Excellent. So we're seeing some good connections here, and I'm noticing some interesting interpretations as well. I like Sue has 10 times 15 and 3 times 15. I think that those are manageable for many, and some of my students it's manageable as well. Counting by 15s can be tough for some students. However, some other students will say, well, it's like counting by 5s, right? So they get that concept in there. But for other students, they might even break it down a little further. So I'm going to show you a slightly different way to break it down. But I think many of us saw that 13 and 10 and 5 were pretty common. However, what I also show students as well is the fact that you can break down the numbers. And I saw this one. I think it was Krishna that had this one up, and I think I may have seen it in one other spot. No, I think it was just Krishna that had shown the 13 broken up as well. And some folks may not recognize this, but when we look at 10 plus 3 in brackets and 10 plus 5 in brackets, this is multiplication that comes up again in grade 10, in both the grade 10 academic course and the grade 10 applied course, that students typically have never seen before. I've heard some refer to this as double distribution, where you're essentially taking the 10 in the first bracket and multiplying it by both the numbers in the second bracket, and the 3 in the first bracket and multiplying it by both numbers in the second bracket. Now, why I think this is so important, especially if we are able to do this early, is that students will then see, in this case, it's very easy to see the 13 broken down into 2 numbers. So it would make sense that both of those numbers are going to have to multiply by everything in the bracket. When students get to grade 10, some students, especially struggling students, really have a hard time with it. And some teachers, I should say most teachers will then give students essentially a trick called FOIL. It's an acronym to help students remember the first term times the first term in both brackets, the outside term times the outside term in both brackets, the inside 2 terms multiply, and the last terms. And there we go, Hester saying the rainbow. Absolutely. So whatever you'd like to call it, essentially it's a trick, it's a memory trick, which works, but a lot of times I feel that students are just doing it, but they don't really understand why. And I think that students can understand why if we start here. Now, most grade 10 teachers that I know don't start here, and I just think they're just not aware of how easy it would be to begin with two numbers to break down. So I look at this as a very, very easy way for students in elementary school to learn to multiply without always resorting to the standard algorithm, which again doesn't necessarily instill any real understanding. This really promotes the idea of area, and it also promotes the idea of understanding what multiplication really looks like. And it gives them a way that they can do math when they forget maybe a more difficult times table. I know a lot of students confuse 7 times 8, 6 times 7, and even maybe 7 times 9. Some of those ones kind of in the middle of the stack or near the end of the times tables tend to confuse students. So maybe if they were to break it down a little bit, it might make things a little easier. So as we break this thing down, and I see folks talking about the visualization, I'm glad that you see that, because it can be really, really tough for students to even understand why this whole distribution thing works. So in this case, if we look at the first terms in the brackets, and we multiply those out, that 10 times 10 gives us 100. And something I really don't want to kind of gloss over here is the value of students seeing what 10 times 10 is, or anything squared is, that it physically makes a square. And that's something that I'm constantly trying to get my students to see, is that when you square, we're not multiplying by 2, we are multiplying a side by an equal side. And that will physically give us a square. And if we're doing this visually, I feel that students are going to have a better chance at kind of connecting that knowledge. We talked about taking prior knowledge and connecting to our new knowledge. The more connections students can make, be it visual, algebraic, contextual, all of these different things can help students really solidify their understanding. So as we move through here, the best part is it really doesn't matter the order in which students multiply this out. Some of you may notice a trend here, and I'm going to do something on the fly. I don't even know if you can see this. Maybe you can. But ultimately, I'm just going to put a line here. The best part is that ultimately the chunking is done for the students, right? They're just literally chopping this thing up by sending lines all the way through, as you can see here. So if I was to essentially just draw a line between our tiles, you know, we could call them algebra tiles, whatever you'd like, you can really easily see the chunks that are formed, right? So students don't really have to do any actual work here. It really all kind of comes out in the wash for them, all right? And a couple questions here we have. Aaron says, any good manipulatives for this? I would say that with big numbers, I don't. I have a set of algebra tiles, but I found myself going to more or less drawing it out, like students drawing them out. There is a good link that I'll pull up. It's a algebra tile HTML5 online widget that you can use, which is great. Yeah, I heard that the Cuisinart rods could be beneficial as well. Algebra tiles is probably a great place to start when introducing this concept, like jumping to 13 times 15 is probably not very helpful. Maybe starting with smaller numbers and having them use unit tiles is probably a good place to start to get that concept. And then, you know, introducing the idea of maybe chunking some of those numbers together. So taking those unit tiles and kind of merging them together. So as we build this, I think we're all pretty comfortable here with what we end up getting. We end up getting our different chunks, which end up giving us a total of 195 when we put them all together. And I think, again, the visual really helps students see that every number must multiply by, every number in the first bracket must multiply by every number in the second. So at that point, that would be what I would consider a typical, probably grade 7, 8, maybe even for me, I use it in grade 9 applied. A good little warm-up, seeing where students are. If students are comfortable with this, they might need another practice problem to, you know, to challenge themselves and to really get a conceptual understanding of what's happening. But at this point, if you have, are there any questions out there before we move on? All right, it looks like We are in good shape here, and Louise has shared out a useful link. Excellent. And I'll do my best to share out that that other link I have for you as well as we're going. So that would probably bring us to the end of that Minds On, and we'd start entering in the inquiry piece. So in my class, even though most of the students would come into my class without ever having chunked multiplication or used the area model in such a way, they may have used it earlier on, maybe in the junior grades, with the idea of area, but not too many students have used it to actually multiply. So that I would consider is new. However, I've kind of introduced that topic to them. What I then do is I want to take the students and I want to just get them kind of outside their comfort zone slightly, but not enough where they have no idea what they're doing. So what this might look like is the number 6 times 14. So at this point, I would probably have my students chunk it out, and it would look, most students would look something like this. We'd have 6 and 14. The 14 would be chunked up, but here's the deal. When I get them to chunk it up, what I tell them is that I'm going to chunk this up for you. And yes, absolutely, Louise, the zone of proximal development is huge. If you haven't done any reading on that, or you haven't come across that zone of proximal development, definitely check it out. It's kind of like that happy medium for students to be sailing, where it's not too easy, not too hard, but comfortable, and that they can actually do some of their own constructing of their learning. So at this point, what I would say to them is, well, you know the two numbers are 6 and 14. Now, what if I did this to you and I said, I'm going to chunk this down into 6 and then something plus 4. And I put it to the students, and I'm sure we can all guess, right? I don't even really have to put it out to the audience here today. What would that X value be, right? I think we could all see pretty quickly. It was 14 to begin with. Now it's X plus 4, so X must be 10, right? So we begin here, and what I have them do is kind of pretend that they're multiplying this out as a number. I haven't done any work with them with variables. I haven't talked about like terms. I haven't talked about multiplying numbers with variables. I just think, well, if you know that X is 10, but pretend you don't know that X is 10, what would it look like? And most students are pretty comfortable saying, well, that 6x or 6 times X must just be 6x. So it's 6 times a number, right? You and I both know that it is going to be a total of 60. But just to get them kind of seeing what that variable could look like. And then finally, that 6 times 4 gives us our our 24. 6 times 4 is 24. So we get a total. So pretty easy stuff, right? Pretty easy stuff. Now, what I'll have them do at this point is I'll have them think back and just double check their work. If they were to sub in 10, they end up getting a final answer of 84. So really, really easy stuff, okay? So they're getting into it. They're not really overwhelmed here. They know that the answer is 10. Some students might ask you, they'll say, listen, why are we even introducing a variable if you know it's 10? But that's to help them kind of set the stage for the next question. This is where I give it to them and I say, all right, you've got 5 and then some number plus 6. And I again, make sure that they understand that all this is 2 numbers, 5 times some number, except that number has been chunked down, and I'm not telling you what the first part of the chunk is, right? So we're getting them, and we're kind of almost gamifying it here, right? You can see, and I never expected this. I literally just did this, this lesson yesterday. Just the timing in the year just kind of worked out quite nicely. But ultimately, getting the students to think about what that number could be and get them really kind of pondering this out. And most students will get pretty far. They might need a little assistance, especially working with the multiplying 5 and x. But ultimately where they end up going, and you might even choose to chunk it down into unit tiles so that students can physically see that 5 times x is going to literally give them 5x tiles, right? And that for me, as a high school teacher, is something very, very new to me anyway. It's only been the past few years that I've really discovered the power of algebra tiles and visuals. So after that point, we've got now 5 times 6, and sometimes it can be useful for students to see all of those unit tiles as well, that physically will give you 30 different units. So nice and easy stuff to begin. However, I then introduce a little bit of a hook. And this, for most teachers, everyone I've ever told this particular part of the lesson has been blown away that I haven't touched any solving equations. Now, mind you, this is grade 9 applied, so these students have solved equations in some way, shape, or form since grade 4, but typically they're coming in thinking they don't know anything about math, right? Many students will go over the summer, they'll come back in, and they won't feel like they remember too much. So in this case, I then challenge them and I say, okay, if I know that the total of these two numbers multiplied is 85, what must that x value be? So I'm going to give it to you guys for just a couple minutes. Take a few seconds. You might have to jot this down on a piece of paper. Now you know more than what I'm showing right now. If we were to actually highlight this, every step of this problem is equal to 85, right? So it's really up to you where you begin. You're probably best off to start at the bottom, but I don't tell students that. I let them kind of play with this. So I would love for you guys to try this out. Can you determine what that missing number of x is so that we can determine what were the two numbers that we had multiplied originally, those two chunks? So give it a shot and see what you come up with. We'll give you a moment to try it out. And I should mention as well, why not, you know what, it might be useful for you to explain what it is that you did to get there. It could just be using math or it could be using words. It's really up to you. Nicely done. So we see some solutions coming in. Excellent. I like Sherry. The same method as Mary Jo is always a good one. Now, what I find really interesting about this, especially when I go back to Mary Jo, I would call Mary Jo's solution the typical teacher solution, right? It's the algebraic method. And when I have my students do this, no one does it using algebra. And I love it. The part I love about it is that they're literally looking at it, and I'm trying to help them build that understanding of what it really means. So if we think about this for a second, if this problem, if the entire answer, and can somebody do me a quick favor and say yes if you can you see my actual cursor, like my arrow on the screen at all? Is that something that you can see when I'm screen? Oh, perfect. So this does make sense. I've been doing this all along and I'm wondering if you can see it. So looking at the interior of this little multiplication or area array model, knowing that that entire rectangle represents 85, getting students to see that these 30 are part of the 85 has been so helpful for me, right? If I take 85 and I take away those 30 unit tiles, I'm left with my 55, which is equal to each of these x tiles. So if we're really thinking this through, like students can get that deep conceptual understanding that this could be broken down into two big chunks, right? Your 5x is equal to 55 and 30 unit tiles is equal to 30 unit tiles. So students can then take that, and a lot of students might even try by trial and error. That's what I find my applied students doing. And only a couple of students will realize that, you know what, if I do that opposite operation, I will get there. So I want to take a second and give you a few minutes to check out some of these solutions. These are fresh off the whiteboard from yesterday when I did these problems, and I ensured that I used the same problems that you'd be seeing tonight so that we could share these out. But you'll see here, this is one student, and notation, probably not perfect. Like, we're definitely not where we want to be, but you can see that there is some thinking going on here, especially the part where we have the 55 plus the 30. And this is my writing on the blackboard or on the whiteboard here, where I was trying to get students to kind of start using a little bit of notation, like, you know, really showing where that information comes from. And moving on to another student's work. So here's another one. Oops, this looks like the same one. Well, that's disappointing, isn't it? Oh, darn, I had another one. Oh, well. We'll get to look at some other student work as we go. Hopefully it's not all the same work. But again, many of those students were doing it in a very similar way. So I'm trying to start them off with a visual prior to getting into anything 2D. So now, the first time I started doing this with the visual model, essentially all I wanted them to be able to do was to use distribution. I had no intention of having them solve equations. However, when I did introduce this concept of this magic number, it like sparked some interest in many of my students. They were actually interested in trying to find this missing piece. And I think partly it was because they want to be competitive, but the other part is the fact that I never told them how, right? Like, if you think about a crossword puzzle or you think about a Sudoku, and somebody says you have to do it with these steps. Here's the algorithm to solve the Sudoku puzzle. You're probably less motivated to do it. Like, you have no intrinsic motivation to solve the puzzle if someone's telling you how to solve the puzzle every single time. I don't know if that makes sense to you guys out there, but to me, it's really struck a chord with me lately that everything I've done in my math classroom has really focused on the idea of me giving you the ability to solve problems. But there is no curiosity there. There is no interest. There is no solving that problem and feeling like you've actually done it. And again, yeah, like Louise is saying with the puzzle, there is no puzzle if you have too much information. So really getting students to think and want to solve the problem so that they can feel good about how they did it and be unique in how they solved it. So I started going, and now we're solving equations for a very, very basic introductory algebra lesson, right? This could be modified, obviously, for any grade level. If you're teaching way down in maybe grade 5 or even in grade 4, some of this is happening in that curriculum expectation we looked at earlier, that you're looking for the missing number. But I think the key is to try to not give students the way or the only way how. What we would do is save that for the consolidation. So here's how a couple other students had done it. I'm not going to keep sending you through the same visuals over and over. I just want to show you some of the other ways that I saw around my room. So here's another student here, ultimately doing what we do with algebra, but in a less organized way. And again, I'm celebrating this with the students that they're very, like, if they can do this, I have many of my students in academic who probably couldn't solve this problem without the algorithm, right? And I think that speaks volumes. Now we're talking about our strong students here, students who supposedly are really good at math, and they're coming up and they can't necessarily explain why they're doing what they're doing. So if we check this out, in this particular case, we've got essentially 9x plus 45 is equal to 99. And this student right away knows that the total minus 45 gives us 54, which is the 9x over here. And that's so important because now if I know 9x is equal to 54, I can then divide in order to find my missing x value, right? And the best part was afterwards is having my students check and saying, okay, what were the two numbers that you chunked? And it was 9 times 11. It's not 9 times 6. 6 was one of the two numbers in the so-called chunking of the numbers. So that was really impressive to me. Here's some more student work. So another student who had done essentially the same thing, but had, I guess a little bit cleaner, not necessarily the the most neat handwriting, but still, you know, a little more organized, a little more orderly. And here's another student who definitely wanted to pose in there, but I knew I'd probably get sued if I left his face in. So unfortunately, I took his face out. And we can see, again, a very similar style. So essentially, they're doing the steps of solving equations, but they're doing it in more of an intuitive way. And I'm trying to stay out of that process right now. Like, it's really taking a lot out of me to not go in there and say, okay, so line it up like this. You should, you know, take away the 45 on both sides. It should look like this. I'm really just trying to get them to build some confidence that they can find the solution they're looking for, and then we'll worry about some of the mechanics later and some of the, you know, formatting later. So again, another solution, pretty standard. You'll see here I was trying to, you know, make sure that they don't lose the concept. This black writing is mine, making sure they don't lose the concept that this 54 is 9x. So that brings us through kind of our inquiry, what we're trying to get them to think throughout the lesson. Like, I want the students solving problems, and Sherry's asking here about lining things up and form. I would suggest that when I consolidate, I show them the algebraic approach, and I show them kind of that, I guess, that more mathy and that more organized approach. However, I'm only recently realizing that it's a really high expectation for me as the teacher to have, for my students to have that, all of that thinking, like there's a lot of deep thinking going on there, to have all of that organized in a very nice package by the end of one lesson. So rather, what I'm doing is I'm using a spiraled approach. I believe I mentioned this in the last session, but I could be wrong, where ultimately I'm trying to spiral through the curriculum where we're constantly coming back to, you know, to readdress concepts and then try to take them a little bit deeper. So during this lesson, I wasn't so concerned about them actually cleaning up that formatting. What I was really concerned about was them being able to solve an equation in some way, shape, or form. Using a variety of strategies is one of those key you know, descriptors in our curriculum. So using a variety of strategies, I want them to be able to use it or to solve that problem using their logic and their intuition. So that's kind of what I've achieved there. However, when we go to make some of these connections and consolidate, I do show them how they can clean it up. But again, I do reiterate to them that this isn't something, like, I don't want to hinder their thinking, and I don't want them to be turned off because they are really into it. And if they're really into it, I don't want them to think, okay, so if my way was so good, why is he telling me I can't do it that way, right? So he's been telling me how awesome we've been doing and how, you know, how intuitive we are and how smart we are, and yet he's saying we can't do it our way, we have to do it his way. So really want to get to a place where I'm hoping that I can get them to almost want to clean it up because it's more organized. I mean, living in an organized house is really nice, but there's a lot of work that goes into living in an organized house, right? So it's something that can't just happen overnight, but something I'd like to build with. And Mary Jo looks like she has a really interesting activity. Absolutely, yeah. Lining up equal signs is awesome. I love it. Right now, I'm at a place, though, you know, just I feel like that activity could be very useful for me, but I don't think it's useful yet because my students aren't even necessarily using an equation. Like, they're, you know, if you see their thinking, it's kind of scattered all over the place. Like, they're not. Even when we're using Pythagorean theorem, and they're using more of that visual model of squaring. So lots of visual going on here, and I'm hoping that I'll be able to, you know, get them comfortable enough with that where we can slowly kind of introduce more of a organized approach to it as well. So, you know, crossing fingers on that one. Now, something else we had done, so when we talk about making some connections, what I wanted to do in this lesson as well, as we were going and how smoothly it was going, I wanted to also get my students thinking about connections they made to previous topics. And one of them is Pythagorean theorem. So if we look here and we were to take two numbers and chunk them up. In this case, I might have, let's say, the number 10 in the first bracket, and now that would tell me x is 5, right? 5 times 2 would be 10, and then over here I'd have 15 plus 2 is 17. So getting students to kind of think that we're still just chunking here, except we have the unknown in more than one spot, which makes things more complex. But I want them to see that when you multiply, again, multiplying x times an x gives you an x squared. So in this case, when we have 2 times 3, or 2x's times 3x's, we end up with 6x's squared. Not 6 squared and an x squared, but just 6x's squared. And you know, getting them to see this has been something that has been pretty valuable as well. So what this does is it really helps my students kind of consolidate some of the learning that they had when we did Pythagorean theorem, when you're squaring sides. Just kind of brings it back and shows that connectedness, and I try to really reiterate that piece. Now in grade 9 applied, they can't solve this equation. If I was to give them a number it's equal to, or the solution, they wouldn't be able to solve because they don't know how to do common factoring, and that's not something that comes up until grade 10 for our academic students. So that's as far as I would take that problem, but I would take something like this, and I would give it to them and see what they come up with. Now this one has proven to be much more of a struggle. However, the students have already built some confidence, so I find that they're willing to kind of work at it a little bit longer. If I was to just hammer this on them, you know, right at the beginning of the lesson, I'd probably lose them all. So what I'd like you guys to do is take a couple minutes here and see, can you determine what the missing magic number is? In this case, we have 2 numbers that have been chunked in a slightly different way, where instead of chunking it into addition, we have chunked it into numbers. And my question for you next would be, is if you do come to an answer, can you give us a little bit of a description of what that, what you did to get there? What was it that you did to get there? Mary Jo says 12 of the x squared thingamajigs. All right. Yes, absolutely. So we're saying in this case, 4x's times 3x's, we get 12x squared thingamajigs. And that has a total value of 300. So if we take it from there and we determine how much one of those x squareds is equal to, we can then get to our root. Nice work there, folks. Looking good. Now again, rather than me drawing this out visually for you, I wanted the students to draw this out for you. And this is what one student, I start here because some of this is awesome and then there's some misconceptions going on here. So I'd like, can you tell me where is a misconception that a student has come up with here? Nicely done. So that 12x squared, we've got that 144, which I'll be honest, when I walked by the board the first time, I didn't even notice it just because I saw 12 and I saw a square, and you know, it just didn't stick out to me right away. But then when I came back around again, I went, whoa. So basically, this student, yeah, has really clearly depicted the 4x's and the 3x's, that they get 12x squareds, and they've indicated that as well. But then now the student's seeing an x squared and they're applying the square to the 12. So there was a good conversation about that. I had another student who did something similar. So in this case, trying to get students to see that, you know what, if you have 12x squareds, just like they have depicted here on the screen, and all of those x squareds equal 300, I try to get them thinking about things like, for example, if I was to split up and just talk about these x squareds. I say, how much do these x squareds equal? And most students are comfortable with going, you know what, that would be 150, and this would be 150. So then I go, okay, well, if this is 150, then how much are these x squareds equal to? And most students might stop, and some of my students might grab a calculator. Other students might say, you know what, that is 75. And I'd say, well, if that's 75, then what would one of these be? And when they get down to that fact that x squared is equal to 25, right? You could just see that kind of, you know, that light bulb go off. And if they know x squared is 25, from there, most commonly students, instead of square rooting, would divide by 2. So a little heartbreaking, but I'm happy that I'm seeing this happen. I don't think I would see these misconceptions like this if I was teaching this more traditionally, like I have been for about 8 years now. So these are some of the things that I saw. And then as I walked around the room, here's a few students. You can see another student with that same visual representation. This student shows, it's interesting because they just, it's almost like this student's not really using the visual as effectively, right? Like the 3x and the 4x look like the same size, and there's not necessarily a full understanding. However, they are trying to work this thing in and determine, okay, what does this really mean? You see a 12 over here. This student, if you look here, this student's actually doing some guess and check, right? You see 30 times 10 for 300. So you can see that they're doing some serious work here, but still kind of focusing on that guess and check. And then Sherry's asking, as you know, would the misconceptions appear as errors on a test or quiz? You know what? If they were clear with their work, like, you know, these solutions are very clear. I'm circulating the room and I'm constantly asking them, okay, why? Okay, why? Really trying to promote them to get as much down as possible. Whereas on something, maybe a test or a quiz, maybe they wouldn't put down as much detail, so it might be tougher to identify. And just having that conversation and hearing them talk to each other is really helpful. Here's another student, and we together had a chat, and I actually was the one that drew this representation over here because this student at first wasn't too sure. This is one of the students that wanted to divide by 2. And eventually figured it out, and we had kind of a consolidation talk together where we essentially drew out the x squared equal to 25, and I had them think about, okay, what must the side lengths be? So so a few different solutions to look at. Here's the last one. Again, this student actually indicates 25 in each of the boxes, which I thought was pretty cool. That's showing a clear understanding that they know what that means. However, again, I don't know if you realized or noticed, but in all of these solutions, I have answers, but not one of the solutions shows a square root symbol or sign. So I'm seeing a lot of activity in the chat with joining and disconnects. Louise, are you still there?
I am, and I'm noticing that too, so I don't know if we're just kind of reaching a peak point in the evening or not, but I would say continue on.
Okay, perfect. I just want to make sure I wasn't talking to myself. That would be a heartbreaker at 9 o'clock if I was all by myself. So few different solutions there for you. So that would be kind of where we're trying to make some connections, really trying to break this down and extend it. And then finally, I would have them do another activity here, trying to dig a little bit deeper. So trying to consolidate, I'd give them some additional practice problems. And then from there, they can figure out where they want to go from here. So just to give